Good afternoon, gentlemen. No ladies, so I have this rule always ladies and gentlemen, but unfortunately I don't have this opportunity to use my common greets. So welcome to our last session of today. And we have 5 presentations, and 3 of them will be done here, and 2 of them will be done online. My name is Wlodek Kulesza, and I am professor, or senior professor even, at Blekinge Institute of Technology in Sweden, in Karlskrona. So it's not so far away, just swim over the Baltic and you will be in Karlskrona. Or you can take the ferry from Klaipeda to Karlshamn, and in Karlshamn we have even one of our campuses. So we have 2 campuses, one in Karlskrona, one in Karlshamn, and from Klaipeda there is ferry to Karlshamn. So the presenters, you know the rules. You have 18 minutes, and after 17 minutes, I will use some sign that is just 1 minute more. If you will not finish, I have some remote controls. I will switch off you totally, so you will be muted by me. We have to keep timing because I think that anyway we started later and we have dinner today, so I think that you need maybe shower after this excitement of presentation, so you need a little bit more time, more than usual. Do you have any questions to me? So the first presentation will be done by Grzegorz Madejski. I know him pretty well because I am one of the co-authors as well. But I still have hidden questions that he doesn't know about it now. So, and Grzegorz, the floor is yours.
Thank you very much. Thank you for your kind presentation. So the title of the presentation is Risk Assessment of Bird Collisions with a Wind Turbine based on Flight Parameters. The authors, as you can see, I'm on the first place, and Wlodek, our chairman, is my supervisor. He's also at the bottom there. And we have 3 co-authors. Those are my colleagues from Bioseco company, a team that I work together with. And we did the research together. So the presentation outline is as follows. I'll introduce the system, something with wind turbines and bird protection. I'll introduce some facts about the company, Bioseco, I work in. Then I will show you our basic collision risk model that works pretty well, but it's pretty basic. And then we'll try to have a discussion about a better model. How can we improve it? What are the problems it can solve? So we'll go through feature selection section of the presentation, collision risk modeling, a little bit of math here, not too complicated, I hope. And we'll conclude the presentation with validation section and some points about future research. So what is bird protection system and Bioseco company? So Bioseco was established in 2013, so we are 11 years old, a pretty young company. By a few students, it was established by a few students from Technical University of Gdańsk. And its main goal was always to protect birds from potential threats of human infrastructure. And I'm talking about wind farms, but also airports. But the main goal is the main goal nowadays. Those are wind farms. So in over 10 years, the company has grown a lot. We've reached international markets. We are in Europe, in Germany, in France, and Spain, but also now in Africa, in South Africa, and in Brazil. Currently, around 50 people work in several departments: engineering, software development, R&D, and administration. And the company is still developing. We have a lot of contracts and future ways of developing. So what is the system I'm talking about? It's a bird protection system, BPS for short. It's installed on the pylons of wind farms, as you can see here in the picture. There is a ring of modules with cameras that are monitoring the sky and looking for birds. If a bird approaches a wind turbine, the system detects it. It has two cameras, so they have stereo vision, and it's able to estimate the distance of the bird. So if the bird is approaching, the system is alerted that there is a possible event of a collision, and it may actually do something by itself. No human intervention is needed. It's fully automatic. And it may send audio signals, so it's very loud. It may send visual signals, a strobe. And if those two actions don't help, it may also stop the turbine. So the rotors of the turbine will stop rotating. The birds will be saved from being hit. Let's look at something nice, a footage, a video from our system. As you can see, the system spotted a bird and it's in a red frame. This is a bird of prey. As you can see, it goes in circles, looks for small mice or food. It's typical for birds of prey, and it's very dangerous for them also because they're looking downwards. They are not paying attention what's in front of them. So it may happen that they don't see the wind turbine blades rotating and they may be hit. You saw it approaching the wind turbine. There is a footage of the same bird, the same occurrence of the same event. And we'll see that the wind turbine is slowly decreasing the rotation speed. It's stopping. And the bird is flying towards it. And just below the blade, it was saved. It flew through the blade area. It's for us, it's maybe strange, but it's a really shocking fact that these blades can rotate with a 300 km/h speed. So it may look slow, but it's not slow. For the birds, it's very dangerous to be around wind turbines. The bird is saved. Also, I need to mention that we want to save not all birds. We want to save only the big birds, the large ones. Those are the birds of concern, of conservational concern. They are important to be saved. There are not so many eagles, red kites due to these collisions. So many countries have administrative laws that want to protect these birds, red kites, eagles, kestrels, buzzards, and so on. So we do not stop the wind turbine when a small sparrow enters the zone. We ignore small birds. So it's a feature of our system and it's okay. So what's the current or the basic risk assessment method that we use currently in our system? It's very simple. It just uses two radii. If a bird approaches the wind turbine in proximity of 400 meters, we activate the audio or strobe deterrence. If it's approaching even more and is within the radius of 300 meters, we stop the wind turbine. Of course, we do it for the large birds, not the small ones. You can also ask, how do we assess the birds? Well, we have to algorithms that based on image processing and stereo vision, so we are able to assess how far and how big, what is the wingspan of the bird, and then we can say if it's a large or small bird. And based on that info, we can just run the collision risk assessment. The collision risk is 0 if it's above, if it's distant more than 300 meters. If it's within this radius, it's collision risk 1. We activate the stopping signal for the turbine. So it's basic, it works well, but of course, there are cases that may be not well processed by the system. This case is okay. You see a bird, it's also a red kite, flying directly at the wind turbine. The wind turbine is the E2 marker in the middle. The red line is the trace or the trajectory of the bird. You can also see some small miniatures, the footage of the bird flying directly at us. And in this case, our model works because, yeah, it's approaching wind turbine. We need to save it. It's within the radius. It's okay. But what happens if we have a case like this? The bird is flying past the wind turbine E1 in the middle. The distance is considerable. It's not flying directly at the wind turbine. So the question is, do we need to stop the wind turbine from rotating? Well, that's the question. Perhaps we need to change the model because the wind turbine was really stopped in this case. So we have two errors that we need to stop from appearing, to mitigate. We have succeeded in diminishing the miss errors. So the rare bird fatality rate has dropped basically to 0. We don't have any dead birds in the wind farms. So that's a good feature of our system. Unfortunately, it stops a little bit too often. So we generate a little bit of the unnecessary energy loss due to false alarms. So as I said just on the previous slide, it was an unnecessary stop. Also, are the wind turbine operators happy with this result? They are happy because they don't have to pay fees for the killed birds. And these fees can be very, very big. In some countries, I think France, it was 10,000 or 20,000 euro for a killed bird. So it's a lot. Also, it's a black public relation problem. If you have killed birds, you're not green energy. So I think it's an important aspect. On the other hand, the wind turbine operators don't want to lose energy due to stops. So there is a trade-off. There is a compromise we need to have. So the research problem arises in this point. We want to decrease the unnecessary energy loss due to the false alarms, but we don't want to have any bird fatalities on our farms. How do we model the risk of collision? How do we assess the risk? And what parameters do we have to choose for the risk assessment problem? So we chose two basic dynamic flight parameters. One, of course, is radius, so the distance from the turbine from the system. It's of course very important for risk assessment. And the second one is velocity, but not the whole velocity of the bird in 3D space, but only the radial component. So we have VR is a radial component of the whole velocity towards the wind turbine or towards the system. So we only look at the speed or the vector component towards or from the wind turbine. As you can see in the two pictures here below, they also have some other technical parameters shown, like the field of view of the cameras pointing upwards. So yeah, but let's move forward. Any other parameters? Of course, we have to check for the maximal velocity of a bird. In a worst case scenario, if a bird approaches our wind turbine, we need to know if it can do it in a short amount of time or not. So for red kites and kestrels, we have 16 and 11 meters per second. And for other birds, we have also estimations from ornithologists. So yeah, so we have to have such info. On the other hand, we also need to know how quickly we want to stop the wind turbine. And in our case, it was 20 seconds. But not always. It depends on the model and weather information and so on. But it was okay for our research. And of course, if you multiply the VR max and T action, you get a radius, a distance, and it denotes the sphere where we want to model our risk. So within this radius, we want to estimate the risk. Outside RT, we are not interested. The risk is 0. And what is the collision risk? Well, it's a function of these 5 parameters. What is this function? I will show just now. the function is very simple. It just takes actually not 5, only 3 parameters. As you can see, we called it danger factor, not collision risk, because risk is typically associated with values from 0 to 1, and our danger factor will be around -1 to 1. So we got it a different name. And it's proportional to velocity, radial velocity of the bird, and divided by the radius of the bird and multiplied by t action, which is a constant value for this wind farm. We also have a extended formula that normalizes this. It cuts all the values that are above 1 and below 1 because those are too extreme for us. So it's just a truncation formula. But the DF is the basic one. Well, below we have a map, which is empty. We have no bird flights on it, but I think I need to share some details about it. It's a map for the purpose of visualization and validation of the risk assessment model. You can see on the x-axis we have R. Maybe you won't see because it's very small. On the x we have R. So towards the left of this map, the bird will be closer to the turbine, right further. And on the y-axis we have danger level. So it spans from -1 to 1. From 0 to 1, meaning the bird will come towards the wind turbine. As you can see, VR and danger level or DF may be negative or positive depending on the VR value. And if the bird is flying away from the wind turbine, a danger level will be negative. We also have some lines on this map, many lines. Those are isotachs, the lines marking the points with the same radial velocity for a bird. And also the last detail, we have colorful lines on the top and on the bottom of the map. Those are uncertainty lines, meaning when a bird flies in the uncertainty area around the 1 value, we get a turbine stop. So if there is a bird that flies towards 1 and it's above this colorful yellow line, we have to stop the turbine. Okay. We also have a collision risk uncertainty modeled. This formula is pretty complicated, so maybe I'll skip details of how it was derived. But some differential differentials were involved in here. It has a lot of parameters. Some of them are from the bird flight parameters. Some of them are system parameters such as baseline, focal length, and so on. Okay, but that's maybe not so important. So we move to validation. This is the result. So we found 4 kestrel cases that the kestrel is a bird of prey. And we put the data from this cases into onto the danger level map. What we can see here is pretty interesting. We were also very happy to see such nice lines. The 4 tracks are marked from trace 1 to trace 4, or T1 to T4. They are marked with dots and with labels. So if you see T1 or T2, those are the beginnings of the track. And the birds fly. And for example, the green line, maybe I'll show this one. The green line will go away from the wind turbine. We are going this direction. And so the danger level is negative because the bird is flying away. We don't have to care about it. And then it started to stop. The radial velocity started to go towards 0. And then just briefly, we had a positive value, meaning that it's just made a circle towards the wind turbine, but then again, changed direction and flew away. The T4 is like a symmetric flight. So the bird is going towards the wind turbine, then it makes just a little circle, maybe it stops, and then goes further. But none of the 4 birds reached the 1 value of the danger level or the uncertainty line just below it. So meaning for this, for birds, there was no need to stop the turbine. What about the red kite? Red kite is a bigger bird of prey. We have 15 cases here. You see some of them are within the risk assessment area. Here is the radius. On the right, we don't have to care about these things. Here we have danger level 0, according to our formula. But one bird, T15, the last one, moved towards wind turbine at a big speed. So we can see it was 7 meters per second, I think, or 8. And it was pretty close, 200 meters away from the turbine. So this was the case where our system says, it's dangerous, we have to stop the wind turbine. It reached danger level 1. Okay. For future work, well, we have a simple basic validation. We need more cases, so we are looking for additional nice database. It's a little bit tricky because we have to cooperate with ornithologists. We need data that is labeled, so we want the species of birds added to the database. We may refine our model and add some additional parameters such as weather conditions, such as bird behavior features, maybe if the current model doesn't sustain a thorough validation. So this is our plan for the coming months. Yeah, and that's the whole presentation. Thank you very much. I'm open to questions.
Okay, thank you very much for very nice presentation. I hope that the audience could understand all issues. So now
I tried to put as little text.
Yeah, it was because we expected your complaint that it is too long.
Okay.
Yeah.
Thank you. You are right. What about the night? You know, a few birds flying on night. You know.
When we are not
really recognize it.
Yes, we are not able to monitor birds at night, but there are not many birds that fly in the night.
Yeah, I understood, but you know, the few one most
Yes.
one are flying. Yeah, but however, you know, there are radar 76, 81 gigahertz.
Yes.
They're watching, you know, 300, 400 meter.
Yes.
Perfect for you, very small site, you know.
Yes, we know that there are radar technologies that can be applied to our system, and we are currently talking about it with a few companies, one from Poland, and we will probably incorporate this technology in offshore wind farms, because they needed more scanning area around them.
The second question is, you have your one wind turbine and one system, or it is all of the wind turbine has, you know, their own system, and you also can connect them, for example, using Wi-Fi as a network.
Yeah, they can be connected, yeah, but they work separately. So each turbine it's not synchronized. I know it could be potentially good if they exchanged some information about bird flights.
More complex, but more.
Yes.
Yeah. This is a very good one. You know?
Yeah, but
presentation.
Yeah, we actually got money for development of offshore, because offshore is totally different, because here the birds don't fly during the night, but the migration birds on the sea, they can fly in it. So we have many different sensors, including radars and so on, because also the offshore wind farms are very big, huge. So it needs much more time to stop it. Mm-hmm. So you have to recognize birds already 1 kilometer from wind turbine. So this is totally different system than Grzegorz presented today.
Yeah,
so maybe after 2 years, we will come with a new presentation.
Offshore.
Hopefully, Grzegorz will be doctor in that time. So
I hope so.
Any more questions?
Yeah, maybe.
Do you have any other system that stop the wind turbine, for example, using 70 megahertz where the birds are sensitive? And radiate them, there are a few paper about, to some birds sensitive for radiation. Radiation. And if you started to radiate, then they are flying up.
You mean electromagnetic or something?
Yeah, some 70 megahertz.
But we have some limitation due to ornithologists. We cannot.
Yeah.
But
stress birds.
Yeah, it's not stress,
Still, and birds, even their sound, after some time, they used to hear it, they don't react.
I know. This is okay, but at least you can combine, and I think there is a few frequencies where they are sensitive, and you can.
Yeah, I actually did some research. I tried to find some devices that could do it. I'm not sure if I found anything. I don't think so. But then again, I consulted the boss, and he said yes, but they emit something, and a lot of authorities in many countries say they must not be noisy. They cannot emit anything. People will complain, authorities will complain. So
speak about the milliwatt.
Maybe.
Okay.
Will you take care also for small birds?
Okay.
For small.
From which size?
I think the size where we distinguish small from big birds is around 1 meter something, 50 centimeters. Yeah.
I think that afterwards, during the dinner, you can ask many questions because they are very interesting.
Thank you.
And the next presentation will be done online from China. Hello, China. Here is Lithuanian. How are you? Hello, China. How are you?
Hello.
Do you hear me?
Yes.
Are you ready with your presentation?
I can hear.
Okay, please start your slides as a presentation slides because we see it on the screen. Yes, and you know the rules. You have 17 minutes or maximum 18 for presentation. Then we will have questions for you.
Okay.
Good
Good afternoon. I'm Caiping, a master student from China Agricultural University, and we're going to give a presentation here. The title of my presentation is Relative Position Detection of Cluster Tomatoes based on BlendMask-BiFPN. The context of my presentation are shown on this slide, which includes 5 parts. As automation technology for tomato cultivation continues to advance in the world's greenhouses, total tomato production and unit yield will continue to increase in the future. However, with the development of world aging population and the decreasing of workers engaged in agricultural harvesting, the cost of manual harvesting continues to increase, which has brought huge risks to the tomato industry. Therefore, it is inevitable to develop the robot technology for picking tomatoes. Current robotic tomato batch picking methods often focus on the detection of tomato batches and fruit stems, while overlooking the crucial aspect of the relative positioning between the peduncle and the main stem. This oversight can lead to clearance between the robot and the tree trunk during harvesting. To address this, a BlendMask-BiFPN algorithm was proposed for the relative position detection of tomato batches. As a result, this approach significantly reduces the likelihood of clearance between the fruit harvesting robot and the main stem, thus improving the success rate of picking, minimize damage to the tomatoes during the harvest process. So I'm going to be speaking about the main work we've done, as this has 3 parts. First, The BlendMask-BiFPN model is proposed to identify the relative position of the tomato batches with the main stem and camera. Secondly, the BiFPN were introduced into the BlendMask model to improving detection accuracy. Finally, two labeling strategies named full stem labeling and partial stem labeling were proposed to label datasets. What we do first is the data acquisition. In this study, to ensure sample diversity, the images include 2 weather conditions and 3 periods of the day. The figure shows some samples of the dataset in different environments. 2 different strategies were used for the labeling, as shown in the figure. According to the position information of the cluster tomatoes relative to the depth camera and the main stem, the samples are divided into 8 categories for labeling. The schematic diagram of the relative position classification of the tomato batches is shown in the figure. Then the next step is to construct a BlendMask network. BlendMask presents the limitation of resolution typically imposed by top-level sampling, resulting in superior mask quality. The architecture of BlendMask encompasses a detection model to assign bounding box to each detected object and a mask branch. This branch adaptedly combines low-level spatial data with high-level semantic information to create precise instance masks. The BlendMask uses FPN for feature extraction and fusion, which results in low recognition accuracy for the relative position of the tomato batches. Unlike the FPN structure, BiFPN removes loads with one single input based on pennant, improving the efficiency of the model. Furthermore, BiFPN uses weighted feature fusion to fuse input feature layers of different resolutions, and the weights corresponding to input layers of different resolutions are also different. The BiFPN network uses a faster normalized fusion method to fuse weighted features, as shown in this familiar. Mask evaluation metrics include AP50, AP75, AR15, and AR75 as shown in table. Details of the experimental platform and model parameter settings are shown on the slide. First, we analyze the experimental results corresponding to the 2 labeling methods. The experimental results of the full stem labeling method are better than the partial stem labeling method, but the mask of PDACO is incomplete in the prediction results of the full stem labeling method, which is not conducive to picking tomato batches. So we choose the partial stem labeled dataset for the following experiment. To verify the effectiveness of the model improvement method proposed above, we use the 3 resonant 15 FPN, resonant 101 FPN, and resonant 100 BiFPN by backbone networks to carry out ablation experiments based on the BlendMask model. Both tables on the slide show the BlendMask model performing best after BiFPN introduction. In addition, we also compared the BlendMask-BiFPN with the current mainstream instance segmentation algorithms, and the results show that our model is better than them in terms of detection accuracy, but the detection time is not the best. To evaluate the performance of the proposed model under different illumination angles, this study conducted the experiment using 176 tomatoes with front night conditions and 181 with back night conditions. The result indicates that the proposed model is not affected by changes in lighting within the greenhouse environment. To evaluate the performance of the proposed model under different occlusion conditions, it is divided into light and moderate occlusion according to the degree of occlusion of the market area. The results indicate that the algorithm proposed in this study did not correctly predict the relative position of the tomato batches when the occluded area exceeded 30%. Lastly, we present a brief summary of the conclusions derived from our research, highlighting the following 4 key points. BiFPN can effectively improve the feature extraction ability of the model. The partial stem labeling method has a better prediction result than the full stem labeling method, and the mask is complete. The proposed model has a better detection effectiveness than the original BlendMask algorithms in terms of accuracy. Future plans involve focusing on address this limitation by expanding the diversity of the dataset to improve the detection accuracy. Thank you for your attention.
We can applaud your presentation. Thank you very much, Ms. Gyula. And now you can wait for some questions. I think that we can appreciate the slides that you presented. They were very well prepared. You try to finish it faster and you speak very fast, but we can get some messages. Gentlemen, do you have any question to Ms. Gyula?
I have a question. In the datasets connection sections, why did you take datasets in so many situations?
The diversity of datasets is a key factor in building effective, fair, explainable, and robust deep learning method.
More questions? Maybe I may have a question, please. What is the future work? What is your next step in this research? Because usually we have to propose some next steps, so we didn't see any, please.
My future place is focus on addressing the limitations by expanding the diversity of datasets to improve the detection accuracy.
Okay, more questions? Do you have any implementation field? Do you have any company that will pay you for your interesting research? Do you have any real implementation field or company that is going to use your research?
No.
No, not yet. Because everybody loves tomatoes, so I think that there are a lot of people that want to improve this. Mm-hmm.
Sorry, I can't hear clearly.
Okay, my question is, do you have any company who will buy your results of research, who will implement it and use it directly on the field of tomatoes field? Okay, don't worry.
Hello.
Yes, please.
Hello. Yeah. I am the supervisor from for Caiping, and I can answer these questions. This is related with the project from the future project for the from Chinese government. We have 5-year plan to do the harvesting and delivering robot for tomato in greenhouse. So that is why I let Caiping do some pre-test at this area. Yeah, I hope it can answer this question correctly.
Yes, thank you for your answer. And we have email address eventually if you would like to have some questions for the authors. So, 谢谢.
Yeah, 谢谢. Thank you. Bye.
We have now the presentation in the room, and this will be done not by the person who is listed here, but by Mr. Korsoveczki. And so you know the rules. You have your presentation on the computer. The floor is yours, please.
Dear respected chairman, dear respected audience, thank you very much for can be here. My name is Gyula Korsoveczki from University of Debrecen, Hungary. And I would like to present our project, which is basically a new initiatives in our education of the robot programming and robot education. So if you may allow me, I would like to emphasize the education-based relevancies and contributions of this project. First of all, I'm coming from the mechatronics department, from our engineering faculty, and it is very important to emphasize the beings of the mechatronics. So what is it exactly, and why is it important to us? Because mechatronics has a special approach, engineering approach, and we experience that it's really hard to give to the students this kind of special vision or this kind of special approach. So as you can see, we have different kind of separated scientific areas, such as mechanical systems, electrical domain, control system, and computer sciences. And separately, each of them has its own descriptive language. So for example, we can use the Newton-Euler equations in case of mechanical systems, Kirchhoff equations, Maxwell equations in electrical systems. We have different kind of control algorithms as well as computer science languages. However, it is important to see that the intersection of each of the area has results a different kind of scientific area, which has a different kind of approach. And what is very important, that the intersection of all four area results the mechatronics. So it's a mistake to think that mechatronics engineers are capable of doing almost everything. No, this is definitely not true. The strongest advantage or their strongest skill to think in systems, see the connection, see the interference between the systems. And this is one of the very important approach what this project will emphasize, which is, by the way, Cartesian. So robotic design of a 3 degrees of freedom Cartesian robot system. Highlighting the engineering approach or mechatronic engineering approach is one thing. Reflecting on the Industry 4.0 principles is another thing. Today we are living in the Industry 4.0 and 5.0 area. So that's why it is very important to emphasize the design principles of our students, because how can we be validated if we are not applying those kind of technologies which are existing in the industry, and many times education try to serve the industry as well. So in this case, we are focusing on the modeling and simulation technologies as well as the digital twin technology during our curriculum and during our projects. It is very important to see that this project is based on the V model of the validation model. In this case, as you can see, V model has two different kind of branches. One branch is this one. This is the research and development stages, and as you can see, this is, by the way, the production stage. It's very important that any kind of development starts from defining the requirements. In our project, we did the same. I will walk through on that in a few minutes within. After that, if we have the requirements, we can derive the model itself. The model can be 3D model as well, and it can be mathematical model as well. So in this case, we will focus on both of them. If we have the mathematical model or the simulation model, 3D model, we can put it into the simulation environment to experiment the performances and to see how it responds, for example, to these different kind of inputs, such as a robot. And of course, we have software design and software in the loop. We can put control algorithm to our robot, to our mechanism, such as PID control, as state space control, or for example, sliding mode control as well. And of course, if we found everything suitable, then in the industry, the production stage can happen. In the university or academic area, we are focusing on this kind of branch. This is the main advantage for us. All right. So as I mentioned, this is, by the way, a more semester assignment and project in our university, and that's why this is a design of a complete robot mechanism from A to Z, by the way, if I would say. First of all, the kinematic analysis, so defining the requirements, defining the acceleration values, maximum acceleration values, speed values, and position data are very important. So generally, the photonomy of this whole mechanism. In this purpose, we're using the MATLAB, and in this case, we are highlighting the facts that, for example, the first order derivative of the acceleration is the speed, the first order derivative of the speed is the position, and in this case, the students can see the difference and can see the interference between the mathematical and physical quantities. After we have the magnitude of the photonomy, magnitude of the speed, acceleration, everything else, we are moving forward to the coordinate transformation, which is very important in the industry, in the field of robotics. It's very important to mention that in industrial robotics and any kind of robotics, we have two different kind of coordinates or coordinate domain. First of all, we can talk about the joint coordinates, and second of all, we can talk about the Cartesian coordinates or Cartesian space. In case of joint coordinates, for example, if we have a robotic arm, we can see the different kind of joint angles here, here, and here. For example, the actual values of the given joints are the joint coordinates, and the word coordinates are the 6 degrees of freedom of the end effector. During the motion of the robot, there is a conversion between of them. So joint coordinates are converted into word coordinates are converted back into joint coordinates. And in this case, we can distinguish forward and inverse kinematics. So in this case, the students are stepping from the photonomy into the coordinate transformation, and they are applying the DH conversion, the Dawid-Hartenberg conversion matrix, which is very important. Later on, I can talk about this. If we have the direction, so now we are not talking about only magnitudes of the speed, acceleration, and so on. Then we have directions, coordinates. Then in this case, we can start to design the whole mechanism parts as well. Because in this case, we are trying to focus on the dynamic behavior of the mechanism as well. In this case, it's very important to see that in case of the dynamic simulations, we are starting from the end effector. We are defining that kind of load and that kind of dynamic parameters which are on the end effector, and we are calculating back, for example, torques and force and everything else back to the base of the robot. In this case, as you can see on the graph, payload determination is the first step. After that, we are choosing a gripper to that one, and we are defining each of the axes to that one. As I mentioned, in this case, this project is about a Cartesian coordinate system, a Cartesian robot. There will be a figure about this one. So we have 3 prismatic joints. We have 3 prismatic axes. The z-axis is a electropneumatic axis, which can go up and down. In this case, we have a y-axis and we have an x-axis. Y and x-axis, it's very important. They are electro-servo drives. So in this case, they are focusing on the drives as well. This is definitely this is generally what I explain now. The next step, if we have the whole mechanism, so each of the joints, for example, x-axis, y-axis, and z-axis, then in this case, we can see the maximum maximum value of each of the velocities in the graphs. For this purpose, we are using two different kinds of software. The first software is the MATLAB, of course, and the second software is industrial software, which is related to the given physical components. So, for example, drives. Here you can see in this case, what is important to us are the maximum value of these velocities. So in this case, we can see whether the chosen component are suitable or, for example, not. In this case, in this example, we can see that the maximum speed is 0.1 millimeter per sec, and for example, the maximum acceleration is 0.03 millimeter per second squared. The simulation performs 350 millimeter long trajectory, and in this case, we can see how the velocities and forces are working during this motion. Here we can see the y-axis as well, so every axis can be compared, and it's very important to see that on both of the graphs we have to see the same values. So if the students can see the same values, of course, it means that they are designing, their methodology are good, and in this case, the calculations are good. After they are tested the velocities, accelerations, and positions, they are focusing on the forces and torques as well. This is very important that in this example, what the actuators, motors, servo motors we choose, here we can see that the maximum torque, what can rise in this case, around 45 or approximately 50 Newton meter. And in datasheet, they can see that, for example, it is only 36 Newton meter, what can be performed by the physical actuator as well. And in this case, they need to reconfigure the whole components and the whole construction of the industrial robot. Of course, they can investigate all of the axes, and the maximum value, what is important to us, of course, we can analyze the whole robotic joints, but as I mentioned, now this is not the focus currently in these initiatives. The third axis as well, the z-axis, and if they chose everything else, then this is the physical representation of the Cartesian coordinate or Cartesian robot. We have three different kind of lines, X line, Y line, and Z line. Here we have the chosen gripper, which is a real physical component. Here we have the servo drive for one axis, or for another axis, and the servo pneumatic drive as well. We are using the inventor, Autodesk inventor, for this purpose to assemble this industrial this mechanism. And it is very important to mention that we are trying to choose the requirements to force the students to put those kind of actuators and those kind of physical components into the simulation, which we have physically and existing. So that's why if we have some kind of very, very good, well-designed projects, then we can build it physically as well. And it is very good because in this case, if we have the accurate simulation and if we have the physical representation as well, and if we can realize between of them, for example, the data and information transfer, then in this case, we have a digital twin. And the pandemic and everything else proved that the virtual extension of university laboratories are essential. We have, especially in the engineering education, we have more and more number of students, and in this case, it's really hard to handle number of students with the small number of devices, and that's why, for example, virtual representation of machines and putting some components into the virtual realization can help us to handle the bigger load, what is, for example, rising. And it is very important to mention that in this case, these kind of virtual representations can be added to the virtual laboratories. So we have many virtual devices now, and in this case, we can put or we can compose a virtual laboratory when remote access can be used, for example, for the given industrial robots, or I would say the digital representation of the industrial robots. This project is used, or this project is new initiatives. It was tested already in 2 semesters. The feedbacks of the students was really good. We are trying to, or we are trying to extend the application abilities of this project. For example, continuing this designing procedure in more and more subjects, because as you can see now, it's only the construction of the robot itself. So it is able to be simulated to move left and right, up and down. However, it is not yet controlled, and we have more and more subjects which are trying to integrate this kind of principle. And in this case, once in the one subject the students designed the robot, in the next subject they are designing control to that one, for example, to servo drives. As I mentioned, we are focusing on the PID controller first of all, because it's an easier representation. Second of all, state space model, and on the master level we are trying to integrate the sliding mode control. It's still in progress, the sliding mode control. However, the PID control and state space control are already integrated, and they are continuing this kind of project. It is very important that if they did not invest enough time to the hardware construction and into the simulation and measuring the whole thing and designing, composing the mechanism, then of course they will have more and more problematic in the next semester, in the upcoming semester, the upcoming subjects. That's why in this case we are trying to push them a little bit to focus for the first time into this project, because later on nothing will work. So in this case it's a small trick from the education side. Yes, I think this is what I wanted to present for you. Thank you very much for your kind attention, and I hope that I could serve with some useful facts or ideas for those kind of institutions who are also suffering from this issues in the education, or in the engineering education. Thank you very much again.
Thank you very much. I am very happy, Chairman, because I got so excellent presenters today. So it's really nice to have such good presenters. It was very nice. And I guess that it is some kind of Michelangelo
trying to reflect for
transformation from Michelangelo into the robotics. Gentlemen, questions, please.
We are more from Debrecen, so that's why they are exactly know this project. So perhaps they are not so strange from this with this project. Yes, please.
I just wanted to ask, what sort of models do you construct there as student projects? You said that first it's simulation, then maybe it's going into a development phase in real laboratories. What are the opportunities to learn? What are they doing? Is it all just fun, or are there things done for industry maybe?
Currently, we have industrial contacts and industrial purposes. Currently, we are focusing on the education, so it's a more semester assignment, and now we are focusing to integrate in more and more subjects. Industrial purposes are also very important. We get a lot of hint from the industry that it would be good if we could focus on this one and this one and this one as well. Of course, we are trying to reflect it. It's very important. But first of all, those kind of competencies are the most important. What is expected from us by, for example, the government, the leadership of the university, and of course, the industrial purposes are really important. We have support from the industry, as I mentioned, and as you can see, there is an industrial partner who supports this one, and many servo drives, pneumatic systems are coming from them. This is why I mentioned that we are trying to choose the requirements in order to force the students to use that kind of capabilities and technology. It's a fruitful cooperation between of them. Hopefully more and more support we can get, for example, from industrial partners. We think, and based on the feedbacks, we are hopefully on the right way.
My question, this course is for the mechanical students, electrical students, or you have very special mechatronic students?
Definitely for mechatronic students.
You have such direction program of mechatronics.
Exactly. For mechanical students and electrical students, they have different kind of assignments, which are focusing only means that only just for mechanics or just for electronics. But as I mentioned at the beginning, mechatronic students need to focus on everything. And in this case, they need to see the walkthrough of such an integrated or intelligent device, which includes all four or all three domains. And it's only for mechatronic students. We want to launch optional subject from as well to make it possible for everyone as well. Still requires some time and some more development, but yes.
Do you have any arm robot that
yes.
they can practice? Because I think
yes.
that students, of course, they can learn from simulations.
Yes, this is only one. Yes, we have robotic arms. This is, I would say, if 100% is the whole practice of robot technique subject, this is currently only 30% of the whole one. Later on, we want to reach the 40 and the 50%, but not more than 50%, because experiencing the real physical robots, knowing how to handle the teach pendant, how to avoid singularities, and so on. In the next presentation, I will talk about this. Is crucial. So we don't want to reduce the portion of the real physical contact and real physical practices.
Okay, I think that we can applaud once again to the excellent.
Thank you very much.
He needs a little bit to rest because he has another presentation soon, so we cannot kill him now. We will wait with this one. Thank you very much. And now we have the presentation online from, we don't know, Kingdom of Saudi Arabia, United Kingdom, or India. And who is going to make presentation? Could you introduce yourself? We don't hear you, gentlemen.
Can you hear me now?
Now it's much better.
Yeah. Okay.
Okay.
So
can you show your slides?
Yeah.
We don't see.
I'll also share my screen.
Please share the screen.
Yeah.
And
yeah, there we go.
Yeah, start your presentation. Because we see just the people. Oh yeah.
Can you see it?
Yes.
I will also be standing up out of respect for all presenters who also stood up.
You have too much energy when you are sitting, so you can explore. The floor.
So first of all, you may be asking, who am I?
Yes.
And what am I doing here?
So,
I am Daniel Rimaru. I'm a PhD student at Birmingham City University, and I will be presenting this project on behalf of my entire team. And now you may ask, what is my project? So if there is one thing you're taking away from this presentation, I want it to be this. So we have looked at the current standard practices for diabetic retinopathy detection, and we managed to find out that there is the possibility of using AI technologies to automate the diagnosis process. We have also observed a gap in the knowledge when it comes to remote screening, which is essentially not having to go to a hospital or another healthcare provider to get your diagnosis. And as a solution, we have built an application leveraging an embedded, lightweight, deep learning model. You may ask now, why do we need this? And I also have an answer for you. So, diabetic retinopathy, along with glaucoma and cataracts, are all chronic diseases that gradually damage various parts of the eye and may eventually cause partial or total vision loss, being among the leading causes of blindness. As such, there is the need for detecting those diseases in their incipient phases and possibly prevent further degradation. But manual detection requires expertise and it is time-consuming. So large-scale screening is expensive and difficult to serve, especially in remote regions. And considering the analyzed literature, we have come to the following observations. First of all, deep learning, particularly convolutional neural networks, in short CNNs, are commonly used for detecting retinal diseases, due to them being able to identify subtle features in medical images. Amazing. However, the research seems to be focused on retinal vessel segmentation. In other words, highlighting the retinal vessels and outputting a diagnosis based on them. There were also some experiments that were trying to skip this process entirely, and they had some decent performance metrics. So we know it's possible. Medical datasets, there's also the problem of medical datasets being usually small and unbalanced. And this is due to patient privacy concerns because they're not allowed to share it with other healthcare providers. This means that there is a need to artificially increase the number of images through data augmentation techniques, either through generative adversarial networks, which generate new images that are difficult to distinguish from real ones. So essentially using AI to train more AI, and also using auto-augment algorithms, which are essentially trying to apply several augmentation policies to the dataset, such as flipping the images or rotating them. And when it comes to mobile deep learning models, we have established that MobileNet, especially the third version, has been widely used for mobile deep learning tasks due to its efficiency and that it's optimized for mobile devices, of course. TensorFlow Lite also made this really easy to deploy on Android devices. While MobileNet remains a popular choice, there are also models like ShuffleNet or UNet who are highly efficient, but they're going through the entire process that I mentioned earlier of doing vessel segmentation first and then doing the diagnosis, which takes some extra computing power for no good reason. So our model is really a lightweight version. So we have MobileNet v3. We are featuring 8,000 parameters, 800,000 parameters, which might sound like a lot, but when you're looking at the other models, it's actually really good. So given that there is a need for large screening, AI seems to be a really good solution, considering that it can handle large demand easily. Also, CNNs have proven to be state-of-the-art in terms of artificial intelligence models, being more practical than emergent technologies, such as the vision transformer, which needs a lot of data, which we don't have, while being also more accurate than traditional machine learning techniques. And there's also the possibility of the fact that MobileNet was one of the best candidates simply because we were trying to train our model on a Windows machine. And this means that we are limited to TensorFlow 2.10, and MobileNet v3 works on 2.10. So it's a really good option for us. The dataset we used was called Diabetic Retinopathy Dataset, and we managed to find it from a competition on Kaggle. And we found it to be one of the best things I've ever seen in my life. So the dataset was originally intended to have 5 classes, and we had to merge them into 2 classes, healthy or diseased. And coincidentally, this led to the dataset being balanced, each class having 1,831 images. We also use faster auto augment for improving the dataset, and we effectively doubled the images for each class, having the new images being flipped or rotated versions. You also have an example right here showing what I actually did to the images. When it comes to the mobile application development, we developed it using Kiwi, which is a Python library. As you may know, Android doesn't really like Python, so we had to use Python for Android to convert the code from Python to Java or Kotlin and port it to Android. We also try to create an easy-to-use interface for diagnosing retinal scans, and we embedded our really lightweight model, which was trained on the computer, so you don't have to worry about the training times, so you can just make calls to the model and you're gonna get it really quickly. Considering the hyperparameters, we can talk about epochs, which is essentially the number of iterations a model goes through, the batch size, which is the number of training samples that are being processed together at one time. Then we have the dropout rate, which is essentially the model forgetting what it learned, so we can avoid learning something that making some sort of connections that aren't actually there. Then we have kernel regularizer, which reduces the risk of overfitting, which is exactly what I explained earlier. And we also have the activity regularizer, which helps with generalization. So if the image doesn't quite look like the training data, we can still have a rough idea of what it actually means, so we don't just get a random chance. And then we have the bias regularizer, which, well, avoids bias, so improves the model's robustness. Looking at the results, so when doing the validation, we performed k-fold cross-validation, which is essentially training k models at the same time, each using different sections of the dataset for training and testing. And then we compare them to one another. And this way, we know we didn't just get lucky with the test data being similar to the training data. Then we have the high accuracy values that are showing that the model is consistent regardless of the images we take for training. We have even more results now, and we can see that the accuracy is 96.72%, meaning it correctly classified retinal images as healthy or diseased 96.72% of the time. We also see the model converging at around epoch number 25, which means we could stop early, although we shouldn't because there is the risk of overfitting. So we can see that there was a time or more where accuracy actually fell and then it went back up. That's because it realized it made some connections where there was actually nothing. So it fixed itself over time. Then we have F1, which is a balance between precision and recall, which we can also see that it has a high value. Then we have loss, which represents how far the prediction is from the actual result. So low numbers are showing better performance, essentially. Lastly, we have the confusion matrix, which shows if there is a certain bias towards giving a certain diagnostic. So we can see that if it has a tendency of saying that someone is diseased or someone is healthy, given that our dataset is balanced, we don't need to worry about this as much. But if we didn't have it, then we needed to look at this more extensively. In conclusion, we have a model that is showing promising results with high accuracy, especially considering its size. It may also be improved by giving it more original images, as this will always be better than generated versions. And lastly, there is the potential for use in remote areas that don't have immediate access to specialists or healthcare in general. I have also recorded an application demo over here. I'm not really sure if we have time for it, but if someone wants it, then I can just share it with you. The things you need to know about it is, so we have an Android emulator. We have 2 images already uploaded to it with these eyes. And then we feed it to the application. which has access to our file explorer. We can give it the image, and then it's going to show us the image we've chosen, along with the probability of that eye being healthy or diseased. And I'm also showing that it works on a different phone if we want this. So it works from versions starting from Android 24 all the way to 31, essentially. Other than that, this demo doesn't really have anything. I can share the slides with you if you want to hear my voice for 5 more minutes, if you want. Other than that, thank you for your attention and have a wonderful day.
Okay, thank you very much. We can applaud your presentation, very efficient presentation, just in time. We have here probably many experts in artificial intelligence and CNN, and I expect some questions. Any one of gentlemen is asking question? You may, okay.
Yes. So the first question is about the model. Do you have any other models that you consider training, or is this CNN just the best model you found and you're not going to look for other ones because it's lightweight? So I suppose it fulfills its task in a quick way. The second one is about data sets. I think those data sets in the internet, they are very small and they are not really, well, they're just too small. I think it would be nice to contact, I don't know, maybe hospitals. I know that students in Poland contacted some hospitals and they got data, real data. Of course, it has to be anonymous. It has to have no personal data, but I think it's nice to have some real live data to run the test. That would be great.
So to start off with your second question, this project started out as just a master's project, a dissertation. So I didn't expect it to grow this big. So I didn't have access to just talking to different healthcare providers to get those data sets. Especially given that they're really strict about the privacy of their clients. So it's highly unlikely they even give it to me, especially to someone who's not really that well known in the academic background. And to answer your first question, you can try and use the traditional methods, which might be lighter than using deep learning. You might not get those results that you may want, but you'll get some results. And they're not even that bad. They're around 80-something%, according to the literature. And if you really want to focus on only the performance and maximizing it, yeah, you can start looking at heavier models or even look into different architectures. Just as I mentioned, you can try and see if vision transformers fix your issue, although they need a lot of data. And I don't think anyone is willing to give you that kind of data. All in all, I personally really liked MobileNet V2. I also tried V3. I also tried V2, and I also tried the first one. And I also tried to come up with a custom version, which didn't really do that well. So yeah, you can. I feel like it's mostly trial and error rather than.
Your result is binary, healthy or unhealthy.
Yeah,
most
it's binary.
Cases they have some levels, so it can be some fuzzy logic or maybe some fuzziness should be here applied, because I think that the C is not, it can be alive or dead, but maybe even this is not so clear. So I think that the disease could be several levels, so it is difficult to judge when you say binary, yes or no?
Yeah, there is a reason for this. So the original dataset had different stages as classes, and they were all over the place. So we had a really low amount of images for, let's say, proliferate, DR, and we had more images for first stage. But then I realized that if we really want to prevent this, we should be able to just see if something is wrong. Tell the client that, hey, something is wrong. You need to go to a specialist and get it checked.
But
So
you know,
that
when
is-
you are not still sick, but you get the diagnosis that you are sick, you can die of the fears, you know. So it's
Yeah.
also, you have to be very careful with too fast diagnosis because it can impact some people and so on. Hmm?
Yeah.
But I think that we can applaud your presentation because we still have one presentation more, and you can regret that you are not with us because we are going to have dinner soon. So thank you
I
for
wish I
your
could have some as well.
presentation. Thank you.
Thank you. Thank you. Have a good day.
Have a nice day. The same. So the last, not the least, we have already got the excellent presentation from Gyula, and now he is going to make another presentation. The floor is yours, please.
Thank you very much. I'm a little bit lucky position because I had already 15 minutes to warm up time, and I would like to spare some time for you before the dinner to have a shower or drink some social juice. So I will try to be as much efficient and quick as I can. Thank you very much for being here again. And my name is Korsoveczki still, and I would like to talk about my our second research, which is the kinematic representation of industrial delta parallel robot mechanism. This is not an education-based project, but it's a research project, so it's more suitable for this kind of presentation. First of all, I would like to walk through quickly for the presentation. I will skip the synergy of mechatronics because it was already mentioned. However, I would like to talk about the industrial robots affected by Industry 4.0 and Industry 5.0 because it is the indication motor of this whole project. General approach of kinematic calculations, forward and inverse direction. We already started to talk about this. And I would like to introduce the robot itself, which is under analysis. This is the Fanuc hybrid delta parallel mechanism. And I would like to present the kinematic calculations as well as the experimental results for the singularity detection and hopefully prediction. And finally, take away about the presentation what should be taken away. So let's see. Industry 5.0 and Industry 4.0 are very important. As we know, Industry 4.0 is the keyword. Industry 4.0 is the digitalization. However, in case of Industry 5.0, not the digitalization is the keyword, but the collaboration. And in this case, this affects the industrial robots. We have, of course, if you want to have a collaboration in the industry, we have a special type of robot, which is called collaborative robots. However, being something collaborative means some kind of sacrificing some details. Collaborative robots are not fixed, so they are mobile to the ground. As well as it means that they have reduced accuracy, they have reduced repeatability. And of course, they have reduced load capacity as well. However, the biggest advantage that they are collaborative. So it means that at the same time, on the same object, human and robot can work together. And this is some kind of demand which is stated for the industrial robots as well, because there are some kind of industrial robots which should be collaborized as well. In this case, in this researching area, we have two different kind of researching direction. The first is how we can investigate the interaction between human and robot. In Debrecen, we have an initiative for this purpose. This is the organic human-robot interaction, and one of our professors has an experience in this research area. However, the second topic is the motion analysis, especially for the singularities. This is that direction what I'm also researching and what I can talk about with passion. So singularity is a special kind of mathematical phenomena, which means that the industrial robot during the motion loses 1 degree of freedom. So it becomes incapable of performing the given motion form. It can be dangerous and it can be not. If it is not dangerous, it means that during the working procedure or along the trajectory, the robot will stop and okay, we can restart the robot or we can continue the working form later on. However, there are a special kind of singularity which results unexpected motion. So the robot is going through a longer trajectory, reaches a singularity point, the controller loses the control of the robot, and robot motion becomes unexpectable. It can be harmful not just for the object, but for the humans as well. In this case, researching this kind of direction is very important. What is also important to understand that singularity has mathematical background. As in my previous presentation mentioned, we have two different kind of coordinate type. We have joint space and we have Cartesian space. Here you can see the joint space, so the actual position or value of each of the joints. And Cartesian space reflects on the end effector of the robot. As I mentioned before, continuous calculation happens between the two kind of coordinates during the motion of the robot. If any times dividing by 0 can occur, in this case, it cannot be performed, dividing by 0. In this case, the robot will lose the control. The controller will lose the control about the robot, and this is when singularity happens. So investigating during the calculation every possibility which results dividing by 0 means that we are investigating the reasons of the singularity. If we know where dividing by 0 happens, we know where singularity can happen. If we know where singularity can happen, we are able to avoid and we are able to detect and predict the singularity, which is a demand in the industry. This is our robot, what we are investigating. This is a hybrid delta parallel mechanism, which has two parts. The first part is the delta part, which means that it has 3 arms or leg, or it doesn't matter how we call this. And we have the hybrid part as well. If we would have only this kind of part, it means that we would be able to use only 3 degrees of freedom, which is not effective in the industry, but 6 degrees of freedom, the +3 is produced by this kind of part, is more effective. However, if we have a more combined mechanism, it means that we have more possibilities for a singularity as well. Complex mechanism has more possibility. And why we are dealing with this kind of robot? Because the singularity of this robot is not covered by the industry. And that's why we are developing new technologies for this purpose. Here you can see the robot itself and the motion of the delta part. Here you can see the mentioned delta part, and here you can see the hybrid part. Parallelly chained actuators and serial chained actuators, and here is how it's moving. As you can see, we have a fixed platform, which can be found here, and we have a moving platform, which can be found, by the way, here. And on this platform, the last 3 axes is fixed. That's why I will distinguish based on delta part and hybrid part. So we have 2 different kind of calculation: forward direction, when we are converting from joint coordinates to vert coordinates, and we have the inverse direction when we are calculating from the vert coordinates to the joint coordinates. We have 2 parts, 2 different kind of calculations, so we have 4 cases in this case. First of all, in forward direction of the delta part, we are investigating the singularity possibilities. As you can see, these legs, which are what I showed previously, they are connected from the fixed platform to the moving platform. During the motion, they are representing spheres. The intersection of these spheres results the center point, geometrical center point of this moving platform. If the z coordinates of the 3 spheres are the same, so it means that at least 2 of the legs in symmetrical position, then dividing by 0 can happen during the calculation. So that's one possibility for a singularity. This is the first type of singularity what we found. As you can see, here is the calculations. These are the vectors which are pointing from here to the center point. And as you can see, we have 3 different kind of singularities. When the first sphere equals with the third sphere, so the z positions. When the second and third are equal, and of course, when all of them are equal to each other. Moving forward, we are still in forward direction, so we are converting the joint coordinates to word coordinates, but on the hybrid part, so the actual 3 joints at the end of the robot. In this case, it's a well-described calculation, so there is nothing new in these calculations. However, we have another type of singularity, which is a second type of singularity, when one of the word coordinate, which is the rotation around y line, is p over 2 plus minus p over 2, so 90 degrees. This is a singularity. This is the only type of singularity which is handled by the manufacturer officially. I will show it how. After that, we investigated the forward direction in both cases, delta and hybrid cases. Let's see the inverse direction in case of hybrid part. This is another well-described calculation methodology. In this case, what is mentioned that we have to, during the calculation, we have to define this Jacobian matrix. But we are calculating not with the Jacobian matrix, but the inverse of the Jacobian matrix. If we are calculating with something inverse, it means that in case of matrix, we have to calculate the determinant. Determinant is a number. If the determinant is 0, then we reached again dividing by 0. Here we did not found any kind of singularities. So in this case, we are really, here we found another singularity when the determinant of the Jacobian matrix is 0. This is a symmetrical position, arm position of the robot, which is also important. So until so far, we found 3 singularity opportunities. And the last one is the inverse direction of the delta part. Now, this is the part where we did not find any kind of singularities. So in this case, there is no point when the robot can lose the control when this part is under motion. Here we can see some experimental results. How this happened? We created a MATLAB code which projects the coordinate transformation. So the same mathematical calculation happens within the MATLAB as happens within the processor of the industrial robot. Here you can see the screen part of the robot, and here you can see the prediction of the MATLAB code. We set coordinates and we expected to have a singularity there. We expected a singularity. We got the singularity in case of the robot. So the first type of singularity was confirmed. Of course, we made more and more experiments. Every test was 50 coordinates transformation. Now only one was here introduced. This is another. For the same first type of singularity, we expected to have singularity there, and there was singularity there. So the robot stopped and started an unexpected motion. Of course, because it was planned that this is something what we could handle. After that, if you remember, I told you that there is one type of singularity which is handled by the manufacturer. As you can see, if you remember, I told you that when the roll angle, which is the rotation around y, is plus minus p over 2, it means that we reach dividing by 0. This is overcome. This is solved by the manufacturer because we can never reach the pure 90 degrees of freedom. Maximum what we can reach is 89, and in this case it will have a switch, coordination switch, and in this case it will goes back to 0. It's a simple methodology, so it is called coordinate sweep, and this is handled. However, the rest of them are not. And finally, if you remember, I told you about the Jacobian matrix. When the determinant of the Jacobian matrix is 0, here we expected the singularity, and here we found the singularity. But it's very important that the robot does not tell us what kind of singularity was occurred. Just it stops or start to work unexpectable, and we need to find out what happened and why happened. It is really hard to plan any kind of avoiding technologies or avoiding techniques if we don't know the reason of the singularity. Our code, what we developed, can classify the singularities, can highlight the reason of the singularity. That's why we are able to know how we can overcome in this singularity. we have to change, for example, the coordinate system for one coordinates or anything else. So the next step will be to develop avoiding technologies or voiding techniques for the singularity avoidance. As takeaway, I would like to highlight some fact about this research, because this research is not yet finished. We have more and more potential in it. What is very important that we opened the closed coordinate transformation of the industrial robot. That's why we can project any kind of moving object into the reference system of the robot. So for example, if I observe my motion of the hand with a camera, and if I get the coordinates, these kind of coordinates can be transferred to the own coordinate system of the robot. So with some kind of project, we are able to hand control the robot. For example, based on my hand, which coordinates and which motion was projected into the coordinate system of the robot. This is one point emphasizing the collaboration. All type of singularities was described and detected. The next step is the prediction. If we have a program code, we need to analyze the program code, see the trajectories, and if along the trajectory we can see any kind of point which is close to the singularity, then it can give a notation to us, and in this case we can think about the avoiding this one. And finally, what is very important, that in case of the MATLAB code, we have a big advantage, which is the compatibility. MATLAB has many kind of toolboxes, as I mentioned, and if we have any kind of calculation with the MATLAB, it can be supported by more and more software. Currently, we are planning to use the Coppelia sim, because Coppelia sim can have 3D visualization, and if we have 3D visualization, we are seeing not just numbers, but we are seeing 3D simulation and 3D trajectories. This is what I wanted to present for you. Thank you very much for your patience and kind attention. I hope I still could spare some time for the social juice and for the shower.
Thank you very much. We can upload your presentation.
Thank you very much.
Robots are very important because it is more and more robots, and we have right robots sometimes. So sometimes we cannot distinguish who is robot and who is not.
Yes, definitely.
But any questions regarding this presentation, please? It was quite condensed with mathematics and condensed, so it was maybe difficult to find.
Sorry, I try to.
Second slide I have seen.
Yes.
The second slide I have seen the synergy. I may be mistaken.
Yes, the mechatronic synergy.
I not heard anything about the synergy. Maybe you can put
mechatronics. Yes, this is something I skipped because my previous presentation I talked a lot about the mechatronic synergy, and I knew that I will have another presentation here and try to spare some time. Yes, you're right. I left it in the presentation and I removed the slide. So that's a very, very, very important and right observation.
Okay.
Thank you very much.
Thank you once again.
Thank you very much.
Because you mentioned here inverse direction, I propose that presenters and me, we will applaud public that you came here, because we had to be here, but you didn't need to come here and you came. So thank you very much that you come here to listen our excellent presenters. Thank you very much.
Thank you very much.
And see you at the evening or tomorrow. Evening. Yeah, we have to. Okay, thank you very much.
Thank you very much.